Welcome everybody on Zoom. Welcome everybody in the lecture hall to this new edition of the course Big Data for Engineers. Some of you I probably know from Information Systems for Engineers in the previous semester. Some of you might take this lecture first. Maybe you will take Information for Engineers in the semester that follows. I usually like to start this course with an appetizer. So the introduction is a little bit different than the rest of the course because I'm not just yet getting into concrete things, but just on the very high level. I would like to give you an impression of what we are about to do. So in this course, the goal is to query gigantic amounts of data, like the title of the lecture, Big Data, even if it's a bit messy. And of course, we'll define what messy means. There's a lot of formal characterizations behind this. And at the end, we'll have the RumbleDB engine that was built at ETH that you can use in a Jupyter notebook, and that kind of encompasses everything we've been doing and building during this lecture, right? So this is the language JSONic that we'll see at the end. We will not just learn how to actually do these queries and to learn how to program big data, but we will also learn how it is behind the technologies, the details of how all of these amazing technologies actually work. So it will involve Hadoop. You might have heard it was a big buzzword maybe 10 years ago, now maybe a bit less because now there's Apache Spark and other technologies that are more modern. We'll look into RumbleDB that, as I said, was built at ETH by your colleagues, so students, and the JSONic language. But let's start with scale, because this is big data. So this is actually a picture of a collision at CERN. And when we talk about scale, we can start with hours. So if we take one of us, for example, in terms of size, it's roughly 1-2 meters, right? So this is in the metric system. Now, if we zoom out to the Earth, then it becomes 40,000 kilometers of circumference of the Earth. So you see already a prefix that this is one that people learn in primary school, so kilometers. By the way, this is a round number. Because this was actually defined that way. That's the meter was defined as 1/40 millionth of the circumference of the Earth. But we also have prefixes for that. We can say instead of 40,000 kilometers, 40 megameters. Maybe this is not something you hear a lot, but mega would be the prefix. And if we zoom out now into the solar system, then the distance between the sun and the Earth, 150 million kilometers, that's also 150 gigameters, all the way to Jupiter gives us 1 terameter, and the whole solar system, well, a bit more than the solar system, like the whole way beyond Neptune, we are at 1 petameter. And if we zoom out again, then there's plenty of suns and plenty of solar system, plenty of stars. This is the galaxy, the Milky Way. So this is when we realize that the nebula that we are seeing in the sky, we are in one of them. That's the Milky Way. So this is 1,000 hexameters. If we continue to zoom out, oh no, I can change the prefix here, 1,000 hexameters, 1 zeta meter. And if I continue to zoom out all the way with billions and billions of galaxies, just like the Milky Way, there is a limit that we reach. That's the visible universe. This is just because light didn't have enough time to reach us past this limit. We have absolutely no idea what there is beyond that. We don't even know if it's infinite or not, but we can estimate the size of the visible universe, so what we can see, to be 138 yottameters, right? I didn't account for the expansion. If you actually expand, it can easily be into the 300 or 400 yottameters if you consider that the universe expanded. But basically, yes, 30.8 billion years would be the estimated age of the universe. But this is very big, right? And a lot of prefixes that there were in there. But if we explore the infinitely big, and this is what people do at CERN, that also means that they need to explore the infinitely small. The only way you can understand the universe at these scales is by understanding how it works at the molecular and atomic and even subatomic level with the elementary particles. And actually, it's the same in big data. I like to compare what we do when we manipulate data with physics or chemistry. In data science, we study the data world. In physics, we study the real world, but they have a lot in common. So before we move on, I'd like to test an app that maybe some of you already know, the Edu app. So please open it, download it. If you don't have it already, you can even go to one of the stores to download, or you can go to the browser. It's eduapp-app1.ethg.ch, but you will see in the browser when I open it. So let me do the switching. There you go. This is what I'd like. No, what is your main backgrounds? So you can just pick. I'm giving you a bit more time the first time so that you have time to download. You see the address, right? eduapp-app1, and move that around for the room. eduapp-app1.ethg.ch. While you do that, I forgot to split my slides, so I'm giving you 1 or 2 minutes to download the app and make sure that it works. And in the meantime, okay, let me move back. So normally we can see your answers here. All right, so we have a lot of different backgrounds in here. It's a lecture that's meant for all departments of ETH. We have computer and data scientists, probably continuing education, electrical engineering, computational science, some more into business, statisticians, robotics, environmental sciences, mechanical engineering, and plenty of diverse backgrounds. So thank you very much for this. And now it's going to be quicker because now you're in the app. Just to get an impression of how many of you already took information systems for engineers. Oh, I didn't paste it was, I forgot to take the right version of the question. It's in the next semester, I will explain. So that doesn't make sense, the in parallel option. All right, so we have maybe 1/4, 1/5 or 1/4. Okay, very nice. So now let me switch back. Since now I have split my slides, normally we should land exactly where we were. Exactly. Okay, so this is how it works, right? So for all departments of ETH, I have 2 courses, Information Systems for Engineers. That's basically the good old days of relational databases from the 70s, 80s, a bit of 90s. And Big Data for Engineers, that's what happens in the 2000s, 2010s. And that is right now where we are, right? They can be taken in any order. And Big Data is the computer science and data science master's level course. It's very similar to this one. Except that here I assume that people already know computer science. So if you are a master's student in computer science or data science, you should not be in this course right here. You should attend Big Data in fall. All right. So this is something we forked the two courses 7 years ago, because the first edition of the lecture, we had both computer scientists and non-computer scientists, but it was a bit tough to find the right balance between explaining too much or not enough. So now you're all non-computer scientists. We can explain many things that otherwise are taught in the bachelor's in computer science, but I'm not taking it for granted. So I assume you don't have all of that background, and I'll take the time to answer all your questions and make sure that everything makes sense to you, right? And normally you should be able, after these two courses, or even one of the two courses, to manipulate data in semester thesis, in bachelor's thesis, master's thesis, PhD thesis. So in many different disciplines, you actually have data sets that you want to manipulate. So that should help you. I like to explain the context of data science with this matrix, which is the 4 ways of doing science. So the 2 old ways that have been known for thousands of years, it's mathematics, right? It's just with your brain deriving all the laws of mathematics, even though it took all the way to the 19th century until we reached the modern approach with more formal definitions of continuous functions and so on, smooth functions. I like to say that this is the world as it must be, like it is necessary. The math has to be that way. We can just do it in our brain. Of course, there are philosophers who will disagree, and that's a very interesting debate. But I want to say that as opposed to physics, because physics is basically experimenting. The world could have been different, the speed of light could have been different, right? But we just need to experiment in order to measure the masses of the particles and so on. So here, this is really with experimental approaches, even though, of course, theoretical physics is at the junction between the two. But this is thousands of years old. But very recently, and that's the 20th century, so now it's been probably 70 years that we're doing that. This is all the math, but of computation, how you compute things with a machine, with algorithms and so on. And then it became a theory on the theory. So the whole thing about computer science is looking at it from a meta level and analyzing complexity theory and so on. But this is still something rather theoretical that you can do on a blackboard, a lot of theoretical computer science. But data science is a bit like, at the same time, like physics and like computer science. Physics, because you have to experiment, but the way you experiment is by gathering data and then you query the data. And it's like computer science because we use machines. We don't just use our brains, right? I don't think a lot of people can query petabytes of data just with their brains, right? It would take a lot of time to do it with a pen and paper. So we have machines to help us, right? So we have machines, and this is rather experimental because we try to understand why the world is the way it is and why it is not another way than the way it is. All right, and you see that there was a lot of wisdom already thousands of years ago with Plato, who told us that a good decision is based on knowledge, not just on numbers. And the whole point of querying data is to actually make sense of it and derive information from the data. So now, if we do a quick history of the way that things happen, it's good to have general knowledge about the evolution of databases and data science. Data actually has existed for a very, very long time. I think it makes sense to start with the times where people were speaking with each other, and well, we still are, but I mean, back then speaking was the main way of transmitting knowledge, right? So the stories of what had happened, epic battles and so on, were transmitted from generation to generation by speaking or by singing. There are also people composing songs, and we have many masterpieces and epics of ancient times. And what's interesting is that we have them all over the world, right? For example, in Europe, we have the Iliad, the Odyssey, and so on. We have the Mahabharata and so on. So many different places of the world where we have similar in spirit kinds of telling the stories. But there is a problem with that, is that information can get distorted and lost across as years pass and generations pass. There was an absolutely terrific invention called writing. And that's also a few thousands of years old now. This is the first time that we found a way to actually encode, because that's an encoding, to encode the information in a way that's going to survive without any change for thousands of years. And the proof that it survived for thousands of years is that we still have that today. We actually found these tablets. So there's two kinds of tablets. Basically, they are the ones that tell stories with text. So this is the Rosetta Stone. That's it's famous because of in Egyptology. That's the way that hieroglyphs were decrypted. It has the same thing in 3 different languages there. So they are the ones. Oh, that's, the antivirus has this issue since an update. I just have to click on close regularly. Okay. So this is the first kind of tablet. It's about text telling stories. But there is a second kind of tablet, and actually that gives me the goosebumps every time I see that. This here is a relational database, and it's thousands of years old. This is a clay tablet, and already back then, in these times, people were storing the information as tables. This is so important because this tells us how tables are such a natural thing to do for humans. Right? This is very, very natural. They do not date back to 1970. They really date back to thousands of years back. And what there is in there, actually, these are triples of integer lengths of a right triangle, right? Like 3, 4, 5, when the squares, 3 squared plus 4 squares equals 5 squares. And these are triples. Then it's not simple ones, right? These are already quite elaborate triples, which is pretty impressive that they knew them at the time. And the main use for that was actually to triangulate the lands, because, for example, in ancient Egypt, whenever the Nile was overflowing and then getting back, you need to keep track of who owns what territory. And the way you do that is with geometry and right angles, right? So this is kind of the motivation. But anyway, this is a relational table, and it looks incredibly like some tablets, but tablet in the sense that we have them today, the ones where you swipe. I don't think it works if you swipe here, but it looks pretty much like spreadsheet software installed on a modern tablets. Anyway, thousands of years old. Then came printing. What problem does printing solve? Copying over. Because back then, where we had this and then paper, you needed people to manually make copy after copy if you want to spread information, and you need to start every copy from scratch. The moment we had the printing press, that's already a few centuries old now, with Gutenberg and so on, it's about having these Buchstaben. Actually, the German word Buchstaben comes exactly from this, the idea that you put the letters next to each other and then you just print by putting it with some ink against the paper. And suddenly you could spread thousands of copies or even millions of copies of books. And this is how a little bit after that, the golden age of newspapers, especially in the 19th century, where you could spread information very fast, right? So this is printing. And then came a new revolution, which are computers. Well, mechanical computers are a bit older than that, but the modern computers that massively accelerated probably dates back to the 1940s, the first modern computers. And then with the invention of the silicon-based transistors, this is where things started really, really accelerating. And this is all about automation. Here we managed to actually compute much larger amounts of, to process much larger amounts of data. The origins of computers, actually, the oldest firms, IBM, for example, is one of the oldest computer firms. It was for the US census. It was in order to tabulate and keep track of the data on the population. So that was the main motivation back then. Right. What's incredible is that a computer like that, what you see here, could actually leads to cutting the electricity of an entire city because of the power that it consumes. And yet, this is by several orders of magnitudes less than the phone you have in your hands in terms of processing power. So this also shows the evolution of the speed at which we do things. Okay. And then in the 1960s, we started processing data on these more modern computers using file systems. So this you probably know, right? Directories and files. This is the sort of things you have on a laptop. On a smartphone, this kind of disappears, right? So with the more modern interfaces, we don't really have this abstraction of smartphones, but on laptops, we still have file systems like that, right? But it's not very convenient, actually, to query data directly in files. And this is why somebody had a brilliant idea. And actually, this is why it's considered the start of the history of databases. This is Edgar Code. who wrote a seeding paper, and it's one of the readings, the optional readings on the Moodle of the course. Edgar Code had the idea that we shouldn't expose this to the user. The user shouldn't have to deal with files and directories and write programs in order to process them. Instead, the user should be given a level of abstraction that everybody understands, even easier than pie charts or even plots that, as some studies have shown. And actually, as I showed you with the clay tablets, thousands of years old, a table. The users should think in tables and rows and columns and so on, and that's it. All the rest is hidden. This is called data independence. And data independence, I'm going to say this a lot. But then later came a few other technologies that emerged in the 2000s, 2000s, I think, where we had key value stores that are a very large-scale way of storing data in a way that you can get and put it. So we'll briefly talk about that, even though it's not a material for this lecture. We have column stores that are a way of storing data in tables, but the cells are a bit bigger than in conventional relational databases, and they can be sparse and have many columns. This we'll study in this course. And document stores, it's to store denormalized data. And I'll tell you exactly what it means to have denormalized data. I'll actually spend several weeks talking about that. But basically, the data is shaped like trees instead of being shaped like tables. And that actually can help a lot with very large scales to do this. All right. So this is the history of databases. And really, if you have to remember one thing, it's 1970. 1970 is the starting point of modern databases with Edgar Code and data independence with the table abstraction. Now, big data is a buzzword, at least was a buzzword, because now there's fancier buzzwords today, like, I don't know, AI, ChatGPT, and so on. But 10 years ago, big data was a buzzword. And so it's very hard to define when you have a buzzword because everybody has a different definition. So I'll try to give you one. But first, I want to say a few words about the context in which that happens. You'll see a lot of companies or company logos in this lecture. It's not that I do any advertisement or anything, it's just that this is history. A lot of the technologies were not invented in academia or only in academia, but they were invented with or by companies that had such large scales of data sets to deal with that the conventional systems just didn't work anymore. So this is why a lot of the technologies were invented with or by the industry, right? So I'll try, of course, I'll try to remain neutral and give you all the names when necessary. We, of course, will look at some examples of technologies and so on, but for every technology, there are several to pick from, right? So what I want to teach you is really the core concepts behind the technologies, but then later you can use any. Just need to look at the documentation and see how they map, right? So there's older ones like Google, Microsoft, these are older ones, Amazon, and the recent ones like Snowflake and Databricks are pretty recent, and they are more into data analytics at very large scales, such as Spark actually has to do with Databricks, right? And Yahoo, Meta, Twitter, and so on. Okay, but now, getting back to big data, there is a characterization of big data that a lot of people like to use. It's the 3 V's. And I'm going to go through them: volume, variety, and velocity, the 3 V's. That's an Eselsbrück mnemotechnic way of remembering them. And we'll start with the volume, V for volume. So we have large volumes of data. Why? First, because we can, since we have the space to actually store them, we just do that. We can with software, hardware, infrastructure, we have the possibility to do that. But also because there's value in the data, right? And actually, this is a very interesting topic, also an ethical topic, a political topic, right? Data protection at the moment is in everybody's minds. For example, with the law that is going to be in application in Switzerland, I think in September this year. So it carries a lot of value, but in this course, I'm not discussing the ethical aspect or political aspects. There are courses for that in the guest department, for example, big data law and policy, where these aspects are discussed. In this course, I'm just giving you the technology. But of course, with great power comes great responsibility, so use everything wisely. Another aspect of big data is that having several data sets has more value than just the sum of the data sets. This is actually because of what's called the join. So if you had information systems for engineers, you'll know what a join is. But basically, if you can put two data sets together, that gives you more value than the two of them separately. Another aspect of data sets, for example, for the flight comparators or the hotel comparators, shopping websites that compare across all providers, another aspect that is important is completeness. You want to have data sets that contain all shops or all trains, all flights, all hotels, and so on. So that's also another motivation for large scales. Here's my first assignment to you. I would like you to learn this by heart. You have to know the prefixes. So I'm pretty sure you know the first ones, right? Kilo, mega, giga, tera. I'm pretty sure you know these because in the context of bytes, right? Kilobytes, megabytes, gigabytes, terabytes, and maybe these a bit less, right? Petabytes, exabytes, zettabytes, yottabytes. Rona and Quetta, they're very recent. It's just a few months old. They've been added very recently by the standardization committee. So these are new on the slides. But here's a trick to remember that. Who knows a bit of Greek, or not necessarily Greek, but the roots of the numbers in Greek? Tetra, penta, hexa in Greek. That's exactly, I think, where that came from. They just altered a little bit by removing or making it sound a bit like Greek. So this is how you remember, because tetra is 4, 1, 2, 3, 4 groups of 3 zeros. Penta is 5, 1, 2, 3, 4, 5, and hexa is 6. 1, 2, 3, 4, 5, 6. That's how I remember that. And in fact, this is also similar to 9 and 10, also, the way that it was chosen. So they did it a little bit on purpose so that it kind of sounds natural. It's not quite like Greek, but it's sufficiently like Greek that you will actually remember, right? So it's all just you add 3 zeros every time. And just to give you an idea, what I did with the universe earlier, I'll also ask you the question after that, only went all the way to iota. If you want to describe in meters the size of the visible universe, you are here. You have to imagine that if you go here, you are 1 billion times larger in one dimension. That means, if I got it right, that if you are here, you have 1 quintillion visible universes. Let you a few seconds to imagine how big that is, just so you imagine how far we have pushed the prefixes here. But I think some of the main motivation is to express the weight of Jupiter in grams, that you actually needed more prefixes. All right, so I had another question for you. Going to go here. What quantity of data would you consider to be big data? Gigabytes, terabytes, petabytes, exabytes, what do you think? A lot of you agree. So there is a consensus for a petabyte. This is also what I would say. I would also say a petabyte. The reason is simple, is that terabytes, that fits on a hard drive, that fits on your laptop. So you can do a lot of interesting things, and I'll try to give you a feeling that even at a terabyte, you can use big data technologies, but petabytes is the scale at which you need a cluster of machines, at least today in 2023, right? So this is why we consider it to be big at the petabyte scale. A lot of companies have petabytes of data. Some of them today have exabytes of data. Zettabytes, yottabytes, that's the scale of humankind, right? The data that humankind generated since in the past few years is probably in yottabytes or zettabytes. Just to give you an impression as well, the data, the amounts of data in bits that has been generated in just the past couple of years is as much as since the history of, since the dawn of humankind all the way to a few years ago. Just as much in the last couple of years as in the entire history before. This is the explosion of the amounts of data that we create. Of course, it's a big challenge to query, because when you have a lot of data like that, first there's a lot of garbage. So you need to filter from the noise to pick the data that you're interested in. And and you have to prepare it, for example, for machine learning and so on. And that's quite a challenge right now. There's the topic of data-centric AI that is on the rise, with the idea that you have to prepare and clean your data sets before you can actually use it in a meaningful way. Okay. I'm going to again switch over. And again, if I did my job right, we should land exactly where we were. Okay. So now, no, that's not quite where I want it to be. Trying again with, I think, this one. There you go. So these are the prefixes. It turns out that in computer science, we love to use powers of 2. And actually, for a while, we were using powers of 2 for the like gigabytes and so on. And it comes from the fact that 2 to the power of 10 is actually quite close to 10 to the power of 3 to 1,000. So this is why computer scientists started using this for kilo, mega, and so on. But of course, that was not very clean scientifically, because you have the two conventions, powers of 10, powers of 2. So some people actually came up with a standardization of the powers of 2 in this way, right? So these are the first 8, they are standardized. The last 2, I actually have no idea. I just made that up with a question mark, because I don't think they've been defined yet, but probably they will at some point. So that would be my guess. Maybe they have a different idea, but this will come. But you don't need to worry about that. Just use the powers of 10 for the purpose of this lecture. It's just so that you know, if you speak with computer scientists, if they tell you a kilobyte is 1,024 bytes, then you will not be surprised, right? But technically, we should say Kibi byte today. Okay, that's the volume. Next, variety. Why variety? Because what we learned recently is that tables are not the only shape out there. It's a very natural one, but there's others. And there's 4 other shapes that you can see data in. One of them is trees, and we'll see a lot of trees in this lecture, right? We'll spend weeks on querying trees. It's a form of denormalized data, but I'll come back to that. Then we have graphs. We can also have data organized in graphs with graph databases that have been on the rise, like Neo4j and so on. This is not part of this lecture. I do it with the master's students in computer science, but this is not in this course. And data cubes are another shape of data. If you took big information systems for engineers, that you've seen them already. So this is why I'm not doing them again in this lecture, right? So the 5th one is unstructured, text, images, video, and so on. And this is a whole topic of its own called information retrieval when you actually deal with that. In fact, this is where ChatGPT would be in this context where you deal with texts. Okay, but again, out of scope of the lecture. So this is variety. What do you remember? What do you have to remember? 5 shapes: tables, cubes, graphs, trees, and unstructured. The 5 fundamental shapes of data. I don't know if there's any other fundamental shape. For now, these are the 5. You can never exclude that somebody is going to come up with another one, but basically almost every data set in the end can be mapped back to one of the 5 shapes. Why is this important? Because if you query a data set and you don't get the shape right, you're basically trying to put a square peg into a round hole if you don't use the right database. The consequence is things are going to be slow. You're going to be slow writing your query, and the computer is going to be slow giving you an answer. This is why it's so important to understand the shapes of your data sets. Next, velocity. That's the speed at which we read the data. Checking the time. So how has it evolved in the past decades, let's say? In order to see that, we first have to be aware that data is just generated on the fly nowadays. You visit websites, there's going to be a log and so on and so on. There are sensors. So we just create data as a byproduct of our activities. But in order to show you and motivate big data, actually, because now I'm slowly going to my definition of big data, I'd like to focus on 3 factors: capacity, throughput, and latency. We can call them that way. Capacity is how much data we can store. There's a trick to make this disappear. I think I just need to close, and there it goes. Yeah, just for the lecture so that you see. So the capacity is how much data can you store? For example, on a hard drive, how much data fits on a hard drive? 1 terabyte, 2 terabytes, and so on, right? How much? That's the capacity. Second, the throughput is how fast can you read the data? How many bytes per second are you able to read from your drive? How fast can you transmit data? The third one is latency. How long do you need to wait until you start receiving data? Right. These three are very important, and I'll use them throughout the entire lecture, because this is fundamental to understand that, to understand why systems are designed the way that they are. Why is there a latency on a hard drive? Well, for a mechanical drive, it's just because it's rotating, and you need to wait until the disk actually reaches the place below the reading head. That's the reason why there's a bit of latency. Right. In flash drives, of course, it's a bit less latency than on mechanical drives, but basically there's always a latency. So capacity, throughput, latency. And now we are going to look at these three in 1956 and in 2023. In 1956, that was the year where the first commercially available hard drive was released. It was gigantic. This is like this. The hard drive that you see here is like this. It's 1 meter, 1 meter 50, gigantic. And it had an incredible 5 megabytes of capacity. Can you believe that? I'm going to close the curtains because I think you have lights that is making it hard to read. I think that should help. Is it going to help? That helps a bit, yes. All right. So the capacity, 5 megabytes. The throughput, 12,500 kilobytes per second. In fact, back then, they didn't really say bytes, they said character, because you can kind of store one character in English in a byte. A byte is 8 bits. So 8 bits, that's 256 combinations. That's more than the English alphabet. So this is why this is the motivation. So anyway, you could read 12,500 characters per second from this drive here. And the latency was 600 milliseconds, which is actually huge by today's standards. But again, this huge thing was rotating. So this is an example of one of the, so it's plenty of layers like that, but you know, this rotates. So every time you need to rotate it and wait until it reaches the point that you can read the bytes that you want to read. Right. So this is the motivation for the latency. And again, I put the dimensions, it's even 1 meter 70. That's probably the height of the whole thing. 1 meter 70, 1.5, 0.7. Absolutely gigantic, but today it's in a museum. Nobody stores data on things like this anymore, because today we store it like this. And actually we need to zoom in a little bit. This is the largest available hard drive, not flash drive, mechanical drive that is available today, which has a capacity of 26 terabytes, 26 terabytes compared to the 5 megabytes that we've seen before. The throughput is 250 megabytes per second, 250 million characters per second, and the latency 4.16 milliseconds compared to the 600 milliseconds, right? So of course, it's logical that the latency is slower because it's also smaller, right? So and it rotates probably even faster. So you have a lower latency than before. And the dimensions, it's like this. You have this in your laptops right there. You have, maybe it's SSDs that you have, but some laptops might still have the mechanical ones. I think the mechanical ones today still have a higher capacity than the SSDs. This is why they are still built today, and they are also a bit cheaper. But anyway, this is what we have today compared to 1956, right? So now, how do that compare? Directly jump here. Let's look at the multiplication factor for capacity, throughput, latency. For the volume, so the capacity, I computed it by unit of volume, because you have to also consider that now it's smaller, right? So you actually fit more in less space. So the capacity increased by 200 billion, if I correctly remember, 200 billion times more bits per unit of volume. The throughput is right there. Maybe you don't see it, but Here it is. That's the increase of throughput that we've had since 1956. And the latency here. It's barely visible, but it's there. Because the throughput only increased by 20,000, and the latency decreased, because here we want it to decrease, by 150. Well, the logarithmic scale, what do you derive from that? Well, you conclude that we are in big trouble. We are in really big trouble because we can store enormous amounts of information, we just cannot read it fast enough. And that's really a big deal because that's just, it's a party spoiler, really. So this is why it just didn't work anymore. We couldn't rely on the older technologies because we just couldn't read it fast enough. And just to give you an example of how in big trouble we are, imagine that instead of a hard drive, I'm using a book, 600,000 words in a book, let's say, today. The throughput, I can read 1,000 words in 1 minute. That should be reasonable. And the latency would be getting to the shelf and picking the book, let's say 1 minute, right? But I'm not going to focus on that one. But basically, if you want to compute how much time do you need to read the book, 10 hours. It's just a division, right? 10 hours sounds reasonable. But now, imagine that in 2 centuries, we humans evolved just like computer did since 1956, meaning that the capacity increased by a factor of 200 billion and the throughput by a factor of 20K only. Then you will need to read one book 11,400 years to read one book. This is how in big trouble we are. This is just way beyond anything you can imagine compared to the 10 hours. So we need to find a new way. There's no way, I mean, maybe in 2 centuries they actually lived that long, so they can actually finish the book, but maybe not, right? So how do you deal with that? Well, the answer is with parallelism. Because if you actually take the pages of the book and you distribute the pages to all of humankind, 1 page per person, then you can actually still read it in 10 hours. It's just that you've done it in parallel. This is exactly what we are going to do in big data. And this is why we have plenty of computers in a data center, in a cluster of machines. So we are going to have thousands of machines that are going to read the data in parallel. This is what big data is. And now if somebody asks you, why do we have so many machines? Then you can say, this is because capacity increased much more than the speed at which we can read data. So we didn't have a choice. We had to parallelize and do it on plenty of machines. And we look, but this I'll explain later, the throughput and latency, that's also an issue, the discrepancy. This is solved with batch processing. It's the idea of processing data in batches rather than one record at a time, but I'll come back to that. Okay, so now my definition of big data, big trouble. How can we store, manage, and analyze data when the discrepancy between capacity, throughput, and latency grew so much? This is, I think, what determines what happens with big data technologies in the past 2 decades. That's how I would define it. Okay, now how is it used? Checking the time because you will deserve a break at some point. Still have a few minutes. Well, it's used everywhere. CERN is one known user or consumer of big data because they generate 50 petabytes every year. It's an impressive number of collisions that they record. They even throw it away, most of it right away. They have some sort, I don't know if it's already AI or some more basic programs, but they throw away most of the data and only keep data that is detected at the moment to be relevant. It's still petabytes. And then it's going to be broadcast or shared with the community, and then they can analyze the data, right? But this is to see the amount of data that they store at CERN just keeps increasing. Another way to generate data is to map the sky. So there is this project called the Sloan Digital Sky Survey with the goal to map every single star and galaxy that there is out there just by moving the telescopes and observation devices. And there's been several phases. The phase 4 ended in 2020, and they have 1 billion objects in there. So the goal is to have a 3D map of the universe. But as you can imagine, that's a lot of data in there. This is a paper that we wrote here at ETH in collaboration with physicists to show the impact of the query language you use with the type of data that you are querying. So if anybody is interested or physicists, you can take a look at that. But other than that, maybe after the lecture, because this involves some of the big data technology there, right? So this is just to tell you, finding the Higgs boson is really a database problem. How do you query the data that you have extracted from the Large Hadron Collider. There's data that predates speaking and singing. It's actually the DNA life. We have 3 billion base pairs in our DNA. It's just on 4 letters. Instead of 2 bits, we have the four bases, 3 billion of them. And now we are able to sequence it. We're even able to print. This is what happened with the RNA vaccines, that we are even able to print and control it at this level. This is something else, though. Here it's a picture of CRISPR-Cas9. These are tools to cut the DNA and reconfigure it. It's at the very early stage, but basically now we are at a level that this is almost becoming computer science in the way that we treat it. In fact, the RNA vaccines for COVID, I almost visualize them as a computer program, because it's really just a list of DNA pairs duplicated quintillions of times that encodes the protein that you want to eliminate. All right, but DNA can also be a storage layer on which you can actually compute queries on relational data. And this was done, I think this is 2018, so this is very quite recent, but you can actually store relational tables in DNA and use the chemistry of the DNA to execute relational queries. That's pretty impressive. I don't understand all of the details. There are some people from ETH who are involved in this, but it's pretty impressive, the sort of things that we can do today. All right, so before I move on to the lecture scope, I think you deserve a break. It's 9 a.m. So we'll take 15 minutes of break. I'm just following the schedule at ETH. So I'll see you at 9:15 for the continuation of the lecture. I'll finish giving you the lecture scope, and then we'll do some SQL brush up in the second hour. So I'll see you at 9:15. Thank you.